All right.
Yeah, so I think we'll start exploring the geometry and we'll see how various properties just naturally emerge. At the moment, we're just talking about Schwarzschild spacetime, but the metric is given by c squared dt squared plus 1 over 1 minus r dr squared plus r squared d theta squared plus r squared sine squared theta d theta. And r star is 2gm over c squared. So as you know, the metric is singular at r equals r star. So we're going to just, whatever it is, I'm just going to call this r star. Whatever this object, whatever it is, right? So the spacetime is singular here, and also at r equals 0. You can see that even over here, you would get 1 over 0, which is infinity. So, and this is the exterior region, and this is the interior. Okay? I have mentioned that, although I have motivated this, I have mentioned that this satisfies the Einstein equation. Well, which Einstein equation? The Einstein equation for vacuum. Okay? So this satisfies, Einstein's vacuum equations. So whatever it's describing the space-time with no other matter. This is only space-time. It's only made up of, gravitational variations. Okay? So in the exterior, it's easy for me to set up a time orientation. And I think I used that script tau. It's going to script t. It's just the time component. Why can I do that? Well, for one thing, g t is equal to g mu nu t mu t nu, which is nothing more than, this is only the 0 component, so this is g0 0, which is minus 1 minus r star over r, and this is time-like. When r is greater than r star in the exterior. So this is a time-like vector. And this approaches Minkowski far enough away. And in Minkowski, 1, 0, 0, 0 is a good time orientation. So at least in the exterior geometry, this is very important, mathematically very simple. But this equation breaks down, or this metric breaks down at r equals r star. So we cannot use this metric. Okay, so all I can say is this guy is a good time orientation in the exterior geometry. Are we good? So obviously what we're trying to do is probe what's going to happen as we, throw things into r equals r star. Probing r star using radial time-like geodesics. Just to understand the source of the problem, or of intrigue, you can say. So when I say radial, I mean obviously theta dot squared equals 0, phi dot squared equals 0. Yeah? Now theta dot squared equals 0, phi dot squared equals 0 would also mean the angular momentum of such a geodesic is 0. And I'm going to take a geodesic, an infalling particle. Where is it infalling from? Well, from infinitely far away. So let's say this is infinitely far away, and I'm just going to radially drop it. It is possible to drop it radially because this is a spherically symmetric space-time. If it's a rotating black hole, maybe the object will start spinning. We don't know. But this is spherically symmetric. There's no, you can say, can it go that way? Well, then the argument would be, why would it go that way? No, it cannot. By symmetry, it can only fall radially. I should have drawn a better straight line, but nonetheless, here it is. So the energy parameter over here is, well, infinitely far away. Remember, we talked about it being mc squared gamma. What I would like for it to do is infinitely far away. Let's assume that the particle is at rest. So we stand infinitely far away from this geometry, and then just let go, not flick it, just let go. So that means for this particular radial geodesic, I'm going to pick epsilon equals mc squared. Gamma is 1. When you put all these conditions to equation 5.4, you will get this very simple equation. Because theta dot squared doesn't show up, phi dot squared doesn't show up, t dot squared does show up, but t dot squared is constant because, or gtt times t dot squared is constant because of this energy conservation. So I want you to verify this. This is just algebra. There's no calculus at this point. Now remember, r dot is dr d tau. So I can solve this. I can do this. And you should, let me just make sure it's GM over R. Yeah. So then C d tau equals plus or minus square root R over R star dr. Yeah. The reason it is C is because if I were to create a C over here, I would put a C over here, C squared, and then I'm taking the square root. So remember, 2gm over C squared is what R star is. And the 2 comes from here. Again, this is easy to verify. So then what I'm going to do is integrate this equation. Listen, I'm not going to waste time doing this. You know the integral of that. That's literally the integration I'm doing. So I'm dropping this at some R0, and I'm looking at any R, how much proper time did this geodesic take? Well, when I integrate on this side, I would get C tau at some R minus, actually I took it to the other side, tau of some R0, where it left. Moreover, this is for both, this is just R dot squared. So it describes both infalling and outgoing geodesic. Indeed, it may be possible to stand over here and throw a rock that way. Yeah? So I want to pick the negative solution for infalling. Okay? Because I'm trying to probe the surface. So I would get minus integral of r to the 1/2 is something to the 3/2, 2/3 to the 3/2. So you can see I will get this. I would say work this at home, but you should be able to immediately do it in class just by staring at it. All of you are very quiet on a Friday, and I get nervous when you get quiet. What's going
Are we
on?
louder on Fridays?
Huh?
Are we usually louder on Fridays?
I don't know, but quiet is not good. What are your thoughts? Are we good? How long does it take for this rock to hit R star? All I do is replace this R with R star. Well, I'll get, oh no, let's do it. I'm not going to do it next time. Well, maybe I'll do it next time.
Yes.
So by the time the rock hits this surface, I don't know if there's anything in the surface, but nonetheless, what do I get? Minus 2R star over 3. That's 1 minus that's correct?
Over 3C.
3C. All I wanted to, the main feature I wanted to do is say, point out that this is less than infinity. That's a number. So, you know, I stand 100 meters away from R star and drop it. And when it hits R star, I don't know if I'll know about it, but might be 10 seconds. It's a finite number. Yeah? All right. But now, so I call this section in my notes the problem with time. What I meant by that was the problem with the time coordinate. What is OTOH? On the other hand, I want to see how much t, as in lowercase, time has lapsed. So to do that, I just do this one I have from here. And so that, I don't know why I wrote it. Well, we write it as 2 steps. Minus 1 over C, square root of R over R star. Where did this come from? It came from this.
Oh.
Yeah? d tau dr. So if I bring this over here and draw the C over there, that's that part. So this goes into here. How do I get this one? I'll put that on. I'll put it in there and you tell me where I got this from. R star R to the minus 1. Let me show you why. Recall the definition of epsilon. We have set that to be equal to mc squared. Right? So this is T. So mc squared gets cancelled off, it's just 1 over that. Okay. And so let me integrate. When I say let me integrate, what I mean by that is I'll let you integrate. It's the delta t, which is integral of c dt, which is minus 1 over square root of r star integral. This r has to go into the integral. R to the 3/2 r minus r star dr. And when you do this integral, which I want you to verify, it's a problem. Verifying an integral is easy. You take the derivative and make sure you get the integrand. But it'll be good if you occasionally do routine calculations. It just, if nothing else, it'll bring back memories of your early days with calculus. And there's a satisfaction in computation. Correct? Correct?
Right.
Yes.
This is so then I say, oh, so this is it C delta T or just so this is C of T evaluated at the location R. Let me even do it this way. T at the location R minus T at the location R0. And let me remember to put the C over here. Look at how bad this time looks. And I'm not just saying because it's a longer expression. Nope. As R approaches R star, T approaches what? Look, this is the term that's the problem. This is R star, this is R star. What's the natural log of 0?
It's undefined.
It's minus infinity. Yeah, minus infinity. But thankfully there's a negative here, so it's plus infinity. So if you are on the rock falling into R star, your clock that you carry with you measures your proper time. And it says, oh, about 10 seconds, finite. But somebody far away is just watching you fall in.
Takes forever.
Doesn't ever fall in.
Yeah.
That's not good.
Even because I'm close to falling.
Yeah. But it takes finite time to get as close as you want to. You know, if you say you want to be the 99% of the trip, it'll say 700 seconds. It's like charging a capacitor.
It's like,
Yeah.
Lock.
To fully charge a capacitor, it takes infinite amount of time.
Yeah.
Otherwise, there's a time constant. But there's nothing here. This is just vacuum. Something is not good. Proper time, I believe, because as you fall in, you're carrying it with you, right? You play a Led Zeppelin song, by the time the song is over, you've hit. It's finite. Yeah. We'll leave it there. Just let it just percolate. Brain. Whoa, what's going on? And we know that we have relied too much on light. So let's do the same thing. So maybe this section I called it probing with. Probing R star with. What I mean by that is by a null geodesic. So again, I'm going to use a null radial geodesic. So you take the radial geodesic equation, which means set theta dot equal to 0, phi dot equal to 0, and you should verify it. It's algebra. but I want you to verify it. It is and this is curious. I'll tell you why. And I maybe guess it, why this took a long time to understand. So Einstein's equation, 1915. Schwarzschild solved that very quickly. He was on top of it. That's the first solution to the Einstein equation, right? But to understand what we're about to do took a long time. Because in now doing this, remember, T dot is a constant, right? Oh, I really should say, if I want, I can do this. Along the geodesic curve. This times that squared is a constant. So naturally, if I'm trying to use the geodesic equation, I would set it equal to a constant, and I would carry this through. But that's not the way I'm going to proceed. I'm going to hang on to my time. I'm going to hang on to my time because time here is a problem when you throw rocks. Somehow we know photons are special. Let's hang on to our time and let's see what happens to a photon. Okay? And we're going to end up getting something called an Eddington-Finkelstein coordinate. I don't know who exactly contributed at what level, but this must have been a few decades later. You might want to even look at when they came up with this result. Something very simple like this. It took a while for people to think of it. They just hung on to that time and then made the following observation. Are we good? Seems like smooth sailing, but any questions? No. Okay. So I'm going to solve for here I get c dt. Obviously I got rid of the lambda for the moment. We'll bring it right back in. Plus or minus 1 minus r star over r inverse dr. From there you can get rid of this. Obviously we're going to shine a beam into r star, so we're going to hang on to the minus 1. But for now, I'm just going to keep it on. And this guy's easily integrated. So it is CT. So I've integrated this side, so I need to integrate that side. And again, I'm not going to do integrals anymore. Plus some integration constant, because I didn't do t minus t0 or something. Because what we're going to do, the constant doesn't appear. And when I looked at this equation, I just didn't like this. This is distance. This is distance. This is distance. This is natural log of, I don't know what that is. I mean, you know, but is it just a bad choice? It turns out it is a bad choice, but I can do it. I can write it like that. And then I can use the product rule. Watch this. Finish writing?
No, I'm not just ready. Okay, we're done. You asked if I was finished writing.
Why can I do that? Natural log of A times B is what? Natural log of A plus natural log of B. So here's my natural log of B, this times this, plus natural log of A. But what is this guy? R star is a number.
Have you taken the constant and moved it into the plus or minus?
Huh?
So there's a plus or minus. on the
Oh, right,
outside.
right, plus or minus.
Okay. Is there parentheses missing? You started a parentheses, but you have not ended it.
Ah,
Oh, okay.
but listen, these are all finite constants, I don't care. So, what's this?
It's all constant. Yeah, it's all constant.
Now I like this, because this is just natural log of a number. R over R star has no units, so it's like 7, natural log of 7, times distance. So you get distance equals distance plus distance. Are we good? Okay. And so, this is CT. What the?
I don't think you could do it.
So what I'd like to start with was where we talked about, we found solutions to this as well, but equal to, this is just t plus or minus 1 minus r star over r inverse dr. This is the radial infalling and outgoing geodesic. Okay? This is radial because theta and phi are fixed. So, if you will, these are beams of light that can traverse the Schwarzschild spacetime. And we integrated this. It's not difficult to do. It is CT equals plus or minus R over R star, natural log of R over R star minus 1 plus a constant. All right, so let me try to draw a diagram. R and CT. And this is R equals R star. And if I pick the outgoing geodesic, you can try it. A random geodesic, well, will look like this. This is the outgoing geodesic. I'll try to somewhat color code it. And now remember, we know that these coordinates are bad, correct? So what's happening close to R equals R star, especially with CT, that could be a result of this coordinate. So this is a big danger in general relativity. Just by looking at coordinates, you cannot really tell what's going on at difficult places, because that could be where the coordinate fails. But at least you know where the coordinate fails. And if I look at the infalling geodesic, it does this. So I'm putting infalling. This is, of course, you pick the negative, and as time increases, R has to be more and more negative. And you can see as R approaches R star where it's going to plus infinity. This goes to minus infinity, but it's infalling. There's a negative sign, minus of minus infinity, plus infinity. So if you look at outside of R star, you'll find that, well, life is good, because we are thankfully outside of R star. Because your event horizon is really made up of these light cones. Yeah? Now, if I were to try and graph this, and I will. We'll see some of the difficulties we're going to face that we'll resolve very easily. You will find that the infalling geodesic, the outgoing geodesic looks like this. I don't know where to write yet. And the infalling geodesic is dashed will look like this. I've only seen Schwarzschild coordinate system, so I'm not, and the statement is going to end with a question. On my outgoing geodesics, I could place an arrow. Which way is the beam of light going? In the inside of R equals R star, Schwarzschild works, the coordinate system works fine, but the time orientation does not. Because remember in Schwarzschild coordinates, the tau equals 1, 0, 0, 0 is time-like only for R greater than R star. What's the reason behind it? If you look at ds squared, for example, you would get minus 1 minus R over R star over R. R star over R d ct squared plus other things. Okay, it's a messy. Class, Nathan Hunt.
Hey, nice to meet you guys.
Nathan Hunt class. So this guy is negative for R greater than R star. As a matter of fact, for R equals R star, it's 0. It's maybe like. But for R less than R star, this is positive. This is not even a time-like vector. So we have no idea of which way to place an arrow. Regardless, I know few things. Well, outside we have an orientation. So I know this is future. The future cone. On the inside, well, I know I'll have a light pole, but I don't know which way the future points yet. This is something we have to figure out. So I may have to erase this drawing because of lack of space, but my goal would be, let's see if I can even hang on to it and use only this. I could have made this a little smaller. But my goal would be to figure out which way is future. Okay? And some of the, I have corrected in my notes, I had a dt squared and c squared. So then you would mistake this for gtt. That's not true. The x0 coordinate, if you will, is ct. x1, if you want, is x, or r. In this case, x2 equals theta, and x3 equals phi. But the entire coordinate ct is x0 because it has the same, ct is what we've said as the coordinate. So it really should be ct squared, and it's really this squared. So, and also I had corrected it. I wrote previously the subscript gtt. That works. We know what's going on. But we should be, if we're being careful, and I made this addition, it should be ct, because that's the coordinate. Only then we'll keep track of the powers of c. Now, at some point you get frustrated and you don't know if it is c squared, c cubed, 1 over c squared, 1 over c. Just let c equal to 1 and the problem disappears. There's always a remedy for the ailment. Okay, so now I'm going to define two vector fields that are very important to our analysis of the geometry of Schwarzschild spacetime. I'm going to define vector field N, and you can see where the definition comes from. It's not complicated. It is 1 minus r star over r inverse 1, 0, 0. And N equals 1 minus r star over r inverse minus 1, 0, 0. Any idea where these two vector fields are coming from? Let me explain. See, suppose you see this geodesic, it's light, so there's no proper time. So if you want, you can parameterize the geodesic by some lambda. And if you did, you would have dct over lambda, dr over lambda. Well, these two are 0 in our case. This would be the null geodesic. But what the top equation tells me is that. So if I pick the outgoing vector, this is not alpha, but it's alpha dot. It's the velocity, for velocity. Now alpha is just a curve. Alpha of lambda is ct of lambda, r of lambda, and in general theta of lambda, phi of lambda. For our case, theta dot and phi dot, by dot I mean with respect to lambda, is 0. So if I look at the outgoing geodesic, this tells me, the top equation there tells me this is 1 over r star over r inverse dr d lambda, then dr d lambda, 0, 0, which I can write as I can bring this dr over d lambda outside, and I can write this as 1 minus r star over r inverse 1, 0, 0. So this is the tangent vector that is proportional to the outgoing geodesic. Yeah? So this would be L. And which is infalling? No. Right, it's outside, so I can do this. That's N. So it's a minus over here, that's all. Yeah? So these are both proportional to the geodesics. All right, but these two tangent vector fields are very important to our analysis. I'll try my best till I give up to keep this diagram going. As I said, I shouldn't have made it so big. It takes too much space. Okay, so now what I want to do is create what I'll refer to as the black hole coordinates. One of the purposes of the black hole coordinates would be to penetrate the surface r equals r star without a problem. So I'm going to look at this equation. And for black holes, you can tell infalling is the theme of a black hole, right? So I'm going to pick this equation, CT, you should see where it becomes a plus. Let me see if we're good. R plus R star, natural log, I'm going to drop the constant. I mean, just an arbitrary constant. So if I take the minus and bring it onto the same side, this becomes a plus. Yeah? So, and then whatever is on the left-hand side, I'm going to call it by a new time, CT bar. One thing to note here is what? Along infalling non-geodesics, CT bar equals constant. Why is that? I've answered it for you. Hold on, let me again erase what I wrote. This was what we had before. For infalling geodesic, that's the case. Yeah? I bring it onto this side of the equation, I get that. And then I'm going to call it, this guy, I'm going to call it CT bar, whether it's meaningful or not. So then, if along an infalling null geodesic, this guy is a constant. So we've already name dropped. I've told you what's going on in Las Vegas. So when you get there, you know what's going on, right? So and it stays there too. You see. So we're using the infalling null geodesic, and that's how we're constructing a. We just created a function, but now we're going to call it a coordinate system. So the coordinate system now will be CT bar, R bar, theta bar, phi bar, where this is given by that. This is the same as that. I think we discussed this a little bit. But I want to just, call it by a different name, because one function doesn't matter. Coordinate systems work in a group. Yeah? So this is one set of coordinate system. So this one, CT, R, theta, phi, I'll refer to as the Schwarzschild coordinate system. This guy, I will refer to as what? The black hole coordinate system. So that's very important. Again, we're calling it black hole coordinate system. We haven't discussed what's a black hole. What's that got to do with anything we're doing? So, in your homework, you will construct the metric for the. Again, it's really the invariant interval I'm calling the metric. But if you have one, you have the other. So when you compute the invariant interval in the black hole coordinate system, that's a homework. Using these four set of functions, you will get that this one doesn't change at all. Isn't that kind of curious how geometry works? What you're changing is time. And then you get 2c, I should really do it this way, 2 dct bar dr, really, I should put r bar. All of this will be r, r bar, because there's no r, theta, and phi, it's r, but they're exactly the same, plus r bar squared, theta bar squared, plus r bar squared, sine squared, theta bar d phi bar. So this is what you will get. I want to explain this. this is just bad manners. By this, I don't mean G, T, R is 2. It's actually 1, because this is short for, remember the metric has to be symmetric. So what this tells me is GCTR equals GRCT equals 1. You will verify that this is the metric. When you look at this metric, is there any discomfort? What are the 2 new features you see? So this is just an explanation. What are the 2 new features you see? By the way, let me do this in the notes I've written down separately. Since T bar is the only one that is changed, if you are really good of keeping track of which is which and who is who, you can remove the bars off the other guys. But that is a sin you will have to pay for along the way. So this is bad manners that I must teach you because it is often done this way. But I would not do it that way. I would just keep bars on. But what are the 2 new things that you observe in this invariant interval? Just look at the Schwarzschild. In Schwarzschild coordinates, it is supposed to be the same metric. You're taking the invariant interval in the Schwarzschild coordinate system and transforming it into this new coordinate system we just call, we attach no meaning to it now. We just call black hole coordinate system. There are 2 things you should pick out that you say is surprising. David, look at the notes passed so you can figure out.
Right, we pulled out those constants.
I'm sorry?
We pulled out the, well, not the constants, we pulled out the coefficients.
What do you mean?
We don't have C R star over R bar, nor do we have 1 plus
C?
R star over R.
You don't have
we
what?
still have C. We still have C. But we
Oh,
don't
no,
have-
forget C. There's no harm, but something else about the character of the, let me do this. Yeah, you know, we can set C equals 1. And I could have done this, I don't know why I expanded it out. But this is the invariant interval in the Schwarzschild coordinate system. If you do a coordinate transformation of the same object, you're getting that object. What are the features that are new?
We no longer have a dr squared.
We no longer have a dr squared. That is weird. You go out radially, you have not done anything. Who can move without their clock?
So one more time.
Who can move without their clock ticking?
Light.
Huh?
Light.
Yeah. So this is a feature of we chose R to the radially infalling geodesic, right? So maybe just going through R is just going through a beam of light and your clock doesn't tick. This is a missing feature. We'll see that explicitly. Okay? I've only suggested something. I'll make that very clear. What is another new feature? Thankfully, it's already circled for you.
The addition of 2C.
Yeah. I mean, what's this doing? Time is messing around with space. Which should be complaints about that.
But we already knew that space-time was intertwined. So.
Yeah. So you can already see things that says our course is getting more and more interesting. I say interesting, you say difficult, potato, potato. Yep. So now, let's do this. Recall, what we'll do is we'll take everything in the short shell coordinate system and transform it into the black hole coordinate system. Maybe I'll do one or two for you and go back and forth. So in short shell coordinate system, what was the time orientation? By the way, please verify this, huh? This will flex your computational muscle. This is considered future pointing timeline. And we can do that. R is greater than R star. Because when R is less than R star, we just talked about it. This is not even a timeline effect. I would like to know in black hole coordinate system, what is future pointing time like? I can do that for R greater than R star. I can use this and then just transform it into the black hole coordinate system. So let me do that. So here's my, and I'm going to write it as short shield, but I'm going to put a bar on it to show that I have transformed it into the black hole coordinate system. Anything that is computed in the black hole coordinate system will have a bar on it. And that's easy. We'll do one or two of these. It's x bar of mu, x nu, t nu, correct? Correct. So let's compute zero. So this is CT bar correct? It's the zeroth element. So CT bar, that's the one equation I need. CT bar equals CT. Is that true, guys? Please. Yep, let's take, so it'll have two terms. It'll have dCT bar, dCT, 1, plus, because this has T and R in it, so technically it would have dCT bar, dr, 0. Because T nu does not have a radial component. So this is easy. If I take the derivative, it's the same. Yeah, like this, you can do it for all four. The other ones are so trivial, you will find that indeed, that is the time orientation. But here's a lesson learned. In black hole CS, future pointing time like when what? Because that is only future pointing time like when R is greater than R star. The whole point is to learn what goes on inside, but we're not yet able, but very soon we will be. Let's see. Oh, I gotta do one. I'm afraid I'll make a mistake, but I'm gonna do it. What was my vector field in? It was 1 minus R star. This is the infalling geodesy. Yeah? This is a homework in your notes, but I want to help you out slightly. If I make a mistake, it's your fault. You guys have to help me. I don't have it written down, so check this out. This is, of course, the CT bar coordinate, R bar, theta bar. The radial direction is a null direction. It's a claim, I have to show that. That's true, because there's no dr squared. It is a null vector. Let's verify. Let me at least verify that the zeroth component is zero. Then if I'm brave enough, I'll try the next component. I'm not making this up. I had to write it down. I didn't want to delay so much, but it's worth it. Let's do this. This is CT bar dCt times 1 minus r star over r inverse plus dCt bar dr bar or dr times -1. Is that correct? This is 1. What is this? It's the derivative of that. What's the derivative of that? This is -1, so I'm going to make it a minus.
1 plus
I can tell you what it's going to be.
1 over, well, it should be equal to exactly the opposite of that.
Can you confirm that part? So the 0th time component goes away. The radial component becomes -1. So are we good with this? Questions? You guys are ready to find. We're going to time orient the black hole right now in moments. So I need you to be with me, asking me questions. We're going to tell you which way is future right now. All right. So because of this result, I know this is a null vector. This is a causal vector. So now, another claim. N bar is future pointing null when r greater than r star. If I were to show this, what do I need to show? We know it is null, because we took the null vector and transformed it, and we can just stare at it and tell you it's null, because if I take the dot product of this with itself, I'm going to get -1 squared times GRR, which is 0. Is everyone clear that n is null? Noah? Zachary? Are we good? So n is null. How do I show that n is future pointing? What do we need? Then the rest is like, everything is a simple calculation. You just have to know what to do. What do we need to do? Need to show what?
That the metric times your
Let's do this in the black hole coordinates.
n times n.
This is what it is. The dot product with a future pointing time-like vector should be less than 0. Then it's in the same causal cone. Well, what would it be? The only component of this is G N only has R component, so R CT minus 1 times 1, which is equal to minus 1, and last I checked, so N, this vector, the infalling geodesic vector, always points to the future. You can check that L points to the future here. So now, I need this space. Well, I just erased what I needed. Did that metric that I erased, the invariant integral, did it have a problem at r equals r star? Were there any infinities? No infinities. You will find the inverse of this metric, and you will verify that the inverse of the metric also contains no infinities. The black hole metric does not have a problem at r equals r star. It is well defined across r equals r star. So let me make that very clear. ds squared bh is well defined across r equals r star. So we can use that coordinate system everywhere. In fact, whereas the only place there might be a problem in the black hole metric, r equals 0. Because when you take the inverse metric, you will find r equals 0 looks okay because d theta squared and all of that goes to 0. That's fine. But when you take the inverse metric, you'll get a 1 over 0, and that's infinite. Yeah? So, and we've talked about this, sort of given you hints that r equals 0 is a problem that just won't go away. Yeah? We just hope to stay away from it, you know. It's just put a little ointment on it and just, you know, hope it heals, but it doesn't. It just stays there. Okay, so N is a nowhere vanishing null vector. Correct? We just ordain N as the time orientation. It is future pointing outside r equals r star. It's nowhere vanishing. It has no way it can flip a time cone. So the direction of N is decided to be the future everywhere. So this pair, ds squared bh, or alternatively, I could even put G, H, along with N bar, is referred to, is it 2 Fs? How many Rs? No, one F and 2 Rs?
One.
As the Schwarzschild black hole spacetime. Again, we're just calling it. But we have set up an orientation for it. I would like to, in passing, and this is probably a problem, but we have an expression for L, which you'll verify as well. R star over R, 1, 0, 0. When you take the vector L that I showed you and transform it into black hole coordinate system, this is the expression that you take. You verify this. Okay, so now we know which way is future. I'm going to understand. I really want to see if I can put an arrow on that today. Well, mine was a ton. Which coordinate system is this? Now I'm interested inside R star. Which coordinate system am I defining this vector? There's no bar, therefore it's a Schwarzschild coordinate system. In the Schwarzschild coordinate system, this is the radial component, so it's the falling just radial direction, not in the black hole coordinate system, it's in the Schwarzschild coordinate system. So again, you will show that just like we showed the other ones, -1, 0, 0. This one will show claim looks like we're doing a lot of these claims to show something that is intuitive, but it's very important. Now you tell, so what I'm claiming is, look at this. This is in the Schwarzschild coordinate system, it's negative radius, falling negative r, not in time. What am I claiming? That this vector inside r equals r star is what? Time-like. Negative r is time-like. That's the claim. How do I prove that? What do I need to show? I want you to tell me. What do I need to show?
You would need to show that the metric computation of R bar mu.
What letter do I begin with?
Huh?
What do I write?
G.
What do I write here?
Yeah.
Well, it won't just be BH, so we need to do R. So.
Oh, if you want.
Okay, start with BH then. And then it'll be of R mu. And tau, right? Oh, is it n? Oh, because n is always future point. I see.
I need to show this,
That's less than 0, yeah.
and I need to show what? If I were to show this, let me show this part. This has only R, so I would have G. This is R, because N has only R, so it has to be CT, R bar of CT bar, and -1. This is 1. R bar of CT is R star over R -1 inverse times -1. When R is less than R star, this number is greater than 1. So this is positive. Positive times the negative is?
Negative.
This is true. But this is useless without showing that this is time-like. I'd like for you to show that it is time-like. already know what's going on, huh? What is, we'll do this a little more carefully. I just showed you that this is future pointing. Right? Look at that. This is the radial coordinate system. Yeah, since I cannot do much more in terms of computation, let me take a moment to show you what happened. It's outside the black hole. The event horizon points this way. You can choose to be a sucker and fall in, or you can get on the outgoing train and get out of town. You silently cross a region called R star. Your light cone has tipped over. This is your future cone. And unfortunately, you are fated to fall into your future. In the future, no matter what you do, you can circle around and live a microsecond longer. Theta phi direction. This is future. Which way is it pointing?
Hard is it? Just guaranteed.
This typical space coordinate has become time-like. Causality has flipped. Once you cross this, you are doomed. Not because gravity is pulling on you necessarily. That's a sort of unfashionable way of thinking about it. But you're fated to fall into your future. And your future points to this location. You can live a little longer. You can say, well, I'm going to shed all my mass and I can be a piece of light. Well, that's not long. Might as well just give it up, just enjoy it. Stiff marble. Just fall. Just stand.
So also implying you can go backwards, like backwards in time.
Backwards in time? I don't know how to do that.
Yeah, I don't either. But this is implying you can while you're in this.
Here you can't. Now, it's a good question. You ask, and I have 2 minutes. Suppose you create an interesting space-time. You'll have to be here for Relativity 3. Yeah, I mean, and then you could do this and come back so that you can kill the robot that was sent to kill you.
True.
We know that can be done. I've seen it in Hollywood already. Can that happen? Yes. What could prevent that? Maybe quantum mechanics. But here that doesn't happen. Sorry, this is the way of the future. It's one way to.
Yeah, why does it look like you can go backwards in time, even though your position is still?
You're not going backwards in time. You just have a closed time-like loop. This violates causality.
You're creating 4D space onto a charge point, so it's like CP is decreasing.
And you can also show that if the energy momentum transfer satisfies the dominant energy condition, we talked about strong energy, weak energy condition, then you cannot have, there's a theorem. But that's for another day. Oh, that's not for this year, but there are things that will prevent all of that.